In this video, we're going to learn how to approximate a function using local linearity and linearization. So we're given that f of 5 equals 3 and f prime of 5 equals 2, and we want to compute the linearization, L of x, of the function f at the point x equals 5, and also use that linearization to compute the value of f of 5.1. Alright, so for starters, don't worry about the linearization part. Just think, if we're given that f of 5 equals 3 and f prime of 5 equals 2, then how can we approximate the value of f of 5.1? Well, to gain some intuition for the situation, why don't we plot this on a graph? If f of 5 equals 3, that means the point 5, 3 is on the function. Let's go ahead and plot it. Here is 5, and here is 3, and this is our point 5, 3. So this bit of information here, f of 5 equals 3, that gave us a point that was on the graph. But how about this bit of information, f prime of 5 equals 2? Well, f prime, the derivative, that is the slope of the tangent line of the graph at x equals 5. So really we can say that this here gives us the slope of the function near x equals 5. So here is x equals 5. Why don't we draw in a little line segment that has slope 2 for values of x that are close to 5. So slope of 2 would mean it goes over 1 and up 2. And let's go ahead and plot that in. So here's our line segment. Keep in mind this isn't exactly what f looks like, but around this neighborhood of the point 5, 3, this is approximately what the function f looks like. And really that's all we need, an approximation. We just want to approximate the value of f of 5.1. And to do that, we're going to use the fact that near this point x equals 5, the function looks really similar to a line with slope 2. Alright, so what we want to do is we want to find the equation of this line here that has slope 2 and passes through this point 5, 3. Let's go ahead and draw that line in with some dotted marks here, just so we can visualize what's happening here. This is the line, and that line is our linearization, L of x. To put that precisely, L of x is the line which passes through the point 5, 3 with slope 2. In other words, that is just the tangent line of f at the point x equals 5. So L of x is also known as the tangent line at x equals 5. So let's go ahead and get the equation of the tangent line. Since we have a point and a slope for this line, we can just go ahead and use point-slope form. So point-slope form, we have that y minus the y-coordinate, 3, y minus 3 is equal to the slope, 2, times x minus the x-coordinate, 5. And we just go ahead and simplify. Y minus 3 equals 2x minus 10, then add through both sides. Y equals 2x minus 10 plus 3, which makes 2x minus 7. So there's our linearization. L of x is equal to 2x minus 7. That's the tangent line of the function f at the point x equals 5. Now we want to use this linearization to approximate the value of f of 5.1. f of 5.1 is right a smidge over to the right from our original point. It's somewhere over here. And to approximate this value, we're going to use this linearization. That is, we write that f of 5.1, since the x input is so close to 5, we can approximate this by using the tangent line L of x at the point 5.1. So f of 5.1 is approximately L of 5.1, and sticking in 5.1 in for x, in the equation for L, we just have 2 times 5.1 minus 7. 2 times 5.1 is just 10.2, so 10.2 minus 7, which is equal to 3.2. So there we go. F of 5.1 is approximately equal to 3.2. Looking back, we can sum up this whole idea very concisely. Differentiable functions are locally linear. If you zoom in close enough to the function, it'll start to look like a line. So as a result, If we know the slope of a differentiable function at a particular point, then we can approximate values of the function near that point using that slope in what is called the linearization. Alright, so lastly, before we move on, what is the general equation for the linearization of f at the point x equals a? Let's go ahead and write that down so we can refer to it in the future problems that we do. So, general equation for linearization of the function f of x at the point x equals a, well, that is just the tangent line passing through the point a, f of a, with slope f prime of a. So putting that in point slope form, we have y minus f of a equals f prime of a times x minus a, which simplifies to just y equals f of a plus f prime of a times x minus a, and that means that the general formula is L of x equals f of a plus f prime of a times x minus a. And there we go. There it is. There's our general formula. Alright, so in the next problem, we're given that g of 3 equals 2 and g prime of 3 equals negative 4. We want to compute the linearization L of x of g at the point x equals 3 and use it to approximate the value of g of 3.2. Also, if g of x is concave down on the interval 2, 4, then is the estimation an overestimate or an underestimate? Well, first of all, let's just focus on actually getting the estimate. Let's compute the linearization. But before we do that, let's draw a little graph so we know what's going on here. First of all, we have that g prime of 3 equals 2. That's a point. So the point x equals 3, y equals 2. Our function g passes through that point. And we know that g prime of 3 is negative 4. So that tells us the slope near x equals 3. So in that neighborhood of x, close to x equals 3, the function looks like a line with slope negative 4. So it's going down. Let's go ahead and draw in a little picture of that. So the function looks something like this. Not exactly like that, but it's pretty darn close. To write the equation of this linear approximation, why don't we just use the general formula that we made previously? We know that the linear approximation centered at the point x equals a of g of x is given by g of a plus g prime of a times x minus a. In particular, we're interested in centering our linear approximation at the point x equals 3. So let's go ahead and plug that in for a. So this is g of 3 plus g prime of 3 times x minus 3. G of 3, well, we know that's just 2, and g prime of 3 is just negative 4. So 2 minus 4 times x minus 3. That's our formula for L of x. Alright, so there is our formula for L of x. That's the first part of the question. What was the formula for L of x? Well, here it is. And now we want to use this formula to approximate the value of g of 3.2. Well, 3.2 is right about over here, so we should expect an answer that's a little bit lower than 2. And using our linear approximation, we have that g of 3.2 is approximately equal to the linearization at the input 3.2. So we just plug in 3.2 into this equation, L of x. 2 minus 4 times 3.2 minus 3. Just go ahead and compute that. This is 2 minus 4 times 0.2. 4 times 0.2 is just 0.8, so 2 minus 0.8. And the result then is 1.2. So that is our estimated value of g of 3.2. Alright, on to the next part. If g of x is concave down on the interval 2, 4, then is the estimation an overestimate or an underestimate? Well, to help us with that, why don't we draw a little sketch? And let's do it off to the side here. In this sketch, let's zoom in on this point x equals 3. So we'll draw our point on the function 3, 2. Let's draw our tangent line, which has a slope of -4. So it looks something like this. So that is L of x. And what does the actual function g of x look like here? Well, we know that really close to x equals 3, it looks kind of like the tangent line here. But we're told that on this interval from 2 to 4, the function is concave down. So that means it looks almost like a downward parabola. So the function is doing something like this. So let's go ahead and label that g of x. Okay, so if we want to determine whether the estimation is an overestimate or an underestimate, why don't we go ahead and plot our estimation on this graph and compare with the actual value of the function. Our estimation at 3.2 is just 1.2. That corresponds to this point on the tangent line. This is the estimation. Now what about the actual value of g of x? Well, we don't know that for sure, but based on our diagram, we can conclude that it has to be lower than the tangent line because the function is concave down. It's curving downwards that way. For example, in this function that we've drawn here, the true value is over here. Now, the true value, of course, depends on how we draw our g of x, but no matter how we draw it, it does have to be concave down on this interval. So it does have to be arcing like this. It does have to be below the tangent line, L of x. And as a result, we have that the estimation is higher, larger than the true value. In other words, the y-coordinate of the estimation is above the y-coordinate of the true value, and we call that an overestimate. In a different problem, you might find that the estimation is lower than the true value, in which case that would be called an underestimate. But in this problem, it happens to be an overestimate. Alright, so now we know how to approximate a function using local linearity and linearization. In the future, we'll see some applications of this idea, such as using local linearity to approximate the roots of a number.